Hi, I'm Nathan and I'm here to talk about differentiation, the basics. The method of differentiation goes as follows. You must multiply the power by the coefficient, this is all of the term, and then reduce the power by 1. So if we look at the top right, the term y equals ax to the power of n has coefficient a and power n. When you want to multiply the coefficient by the power, hence you get an in front of the x for the gradient function, and then you want to reduce the power n by 1. Hence, we can express the gradient function as dy over dx is equal to an x to the power of n minus 1. We can use a couple of examples to consolidate this understanding. If y equals 5x to the power of 4, we know that the coefficient is 5 and the power is 4. Hence, dy over dx is equal to 5 times 4, which is 20, x, 4 minus 1, which is 3. Second example, if y equals x to the power of minus a half, we can say that dy over dx is equal to minus a half times by 1, which is just minus a half, x to the minus 1 half times minus 1, which is minus 3 over 2. With this second example, it's key to understand that whilst it is more difficult because it uses fractions and there's actually not a more evident coefficient, the same principles apply. For this example, the coefficient is in fact 1, because in theory we could just put brackets 1 there. But you just don't express it. You express it simply as x to the power of minus a half. It's the same. And then equally, with the power expressed as a fraction, you just treat it as a normal fraction but use the regular method. The uses of differentiation are as follows. You can use it to find the equation of a tangent. So at the point where the tangent meets the curve, their gradients are equal, i.e. it can be explained via this relationship m1 equals m2, where m1 is the gradient of the curve at this point and m2 is the gradient of the tangent. So the tangent is, if you look down here, we can illustrate it on this diagram. It is parallel to the curve at the value x, okay? m1 equals m2. The second use is to find the equation of a normal. At the point where the normal meets the curve, the gradient of the normal and the gradient of the curve are perpendicular. So again, m1 is the gradient of the curve, but in this case m2 is the gradient of the normal as opposed to the tangent. And we can say that m1 times m2 is equal to minus 1. Again, we can illustrate it down here. The normal is perpendicular to the curve at the value x. We can look at a couple of questions to consolidate our understanding in tangents and normals. And this is your stereotypical question about both of them. So it tells us that a curve has equation y equals x to the power of 4 minus 20x plus 1. And it wonders what the equation of the tangent to the curve at the point x equals 2 is. Now, it's asking us to find the equation of the tangent. Now, irrespective of the tangent, when finding the equation of any line, which in this case the tangent is, we typically use this method. We want to find the coordinates along the curve at the point where the tangent is meeting the curve, and we also want to find the gradient of the curve at this point. So, and this can be expressed in the form y minus y1 equals m2 x minus x1. So x1, y1 is just a set of coordinates. So in this diagram above here, it will be this coordinate. It is where the tangent and the curve are meeting. And m2 is the gradient of the tangent, which in this case we know is equal to the gradient of the curve at x equals 2. So how do we find that set of coordinates? Well, we just input the x value into the original equation. So we can say that y1 is equal to 2 to the power of 4 minus 20 plus 1, which is equal to 16 minus 20, minus 2 times 20, minus 20 times by 2, which is actually minus 40, plus 1. So we can say that that is equal to minus 23. Hence, x1, y1 can actually be expressed as 2 minus 23. So we have the set of coordinates. What's next? We need to find the gradient of the tangent, which is equal to the gradient of the curve at x equals 4. So to find this out, we need to work out the gradient function, which is dy over dx equals 4x to the power of 3 minus 20. Now, when tackling a gradient function like this, where there are multiple terms, you simply differentiate term by term. It is as simple as that, as I've done here. To find dy over dx, i.e. the gradient at x equals 2, you simply input the x value into the dy over dx. So when x equals 2, dy over dx is equal to 4 brackets 2 to the power of 3 minus 20, which we can say is equal to 32 minus 20, i.e. 12. So we now have m2 and we have x1, y1. So we can just input into our formula at the top to find the equation of the tangent. Y minus brackets minus 23 is equal to 12x minus 2. And then we can expand this so that we get y is equal to 12x minus 24 minus 23. So y is equal to 12x minus 47 when we simplify it. And that is the equation of our tangent. I just want to quickly note that because I didn't say it explicitly, here we've worked out the gradient of the curve at x equals 2. And because we know that m1 is equal to m2 with a tangent, then we can just simply say m2 is equal to 12. Hence, we can input it into our formula that we established at the beginning. Moving on to part 2, it wants us to find the equation of the normal, in this case, to the curve at the point x equals 2. So again, as is a tangent, a normal is a line. Hence, to find the equation of the normal, we need to find the point where it is meeting the curve and the gradient of the normal at this x value. So, again, we can use the formula y minus y1 is equal to m2 x minus x1. Now, we already know x1, y1, because obviously where the tangent meets the curve and where the normal meets the curve, as illustrated by this diagram here, is the same set of coordinates. So we already know x1, y1 can be expressed as 2 minus 23, and all we need to find out is m2. We already have the gradient function, which is equal to dy over dx equals 4x to the power of 3 minus 20. The only thing that changes in this case, is the gradient of the line, in this case the normal, and you'll see why. So from this gradient function, we've already established that when x equals 2, dy over dx is equal to 12. Now, as we know, this is m1, and the difference in this case is that the relationship between m1 and m2 is slightly different with the normal. We know that m1 times by m2 is equal to minus 1, where m2 is the gradient of the normal. Hence, m2 is equal to minus 1 over 12, just subbing in m1 there. So we now have x1, y1, and we have m2. Hence, we can sub all of this data into the formula to get the equation of our normal. So y minus, again, be careful with the brackets, minus 23 is equal to minus 1/12 x minus 2. This can be written, expanding it, just y plus 23 is equal to minus 1 over 12x plus 1 over 6. We typically don't like expressing as a fraction, so we want to expand it, and in order to remove the fractions, we multiply everything by 12. So we can say that 12y plus 276 is equal to minus x plus 2. And getting it in the form we want, which is roughly y equals mx plus c, we say that 12y is equal to minus x minus 274. And there you have it, the equation of the normal. Thank you very much.